I already claimed that regular expressions and finite automata accept the same class of languages, the regular languages, and in this video we have a closer look at how to get from a regular expression to an equivalent non-deterministic finite automaton. The theorem here says that for every regular expression we have a non-deterministic finite automaton that accepts the same language, so that the language of the expression equals the language of the automaton. That's half of the theorem, which dates back to Stephen Cole-Kleene. For the proof, I have to show how to construct an NFA for a given regular expression. The regular expressions are defined inductively, so the proof will follow this inductive definition for the regular expressions. We start with the basis. For the empty set, it's easy. This actually is an automaton that accepts the empty set. It has only one initial state, no final or accepting state, so this automaton accepts the empty set. For the set containing only the empty word, this is an automaton that accepts the empty word and nothing else. It has only one state, which is initial and accepting. Third basis case is just one letter from the alphabet, and we can also easily construct an automaton for this case. It consists of two states, one is initial, one is accepting, and we have a transition with the letter A from the initial to the accepting state. And so we have an automaton for a regular expression A for each element of the alphabet. Having dealt with the basis, we have now the hypothesis that for two regular expressions E1, E2, we've already constructed NFAs A1, A2 that accepts the languages defined by E1, E2. Having this, we have to construct automata for union, concatenation, and star. First, for union, we already know how to construct an automaton accepting the union of two languages defined by two automata. So we can just apply this construction here, and we obtain a construction to construct an NFA for the regular expression E1 plus E2. Similarly, for concatenation, we already know how to do concatenation for two finite automata, and we can just take this construction and apply it here, and we get an automaton for the concatenation of L of A1 and L of A2, which is exactly the language defined by E1, E2. And the same argument holds true for the star. We already know how to do this as well, and we can just use this construction here. Let's have a look at an example. Let's try to build an automaton for this regular expression A plus B followed by B and the whole thing starred. First, we get three automata for A, for B, and another one for B, for each of the letters occurring in the regular expression. The first operation we have to consider is the innermost operation, and the innermost operation is union, so we construct an automaton for the union, A plus B, using the construction we have defined for the closure properties. After having dealt with the innermost operation, the union, we proceed to the concatenation, so we have to construct an automaton for the concatenation A plus B concatenated with B, and we do the concatenation construction. Concatenation construction simply says taking every transition that leads to a final state in the first automaton, this is this transition here for example, and we duplicate it and add a transition to the initial state of the second automaton. There was another transition leading to an accepting state. There was this one here, the B transition, and we have to duplicate this as well and make a transition to the initial state of the second automaton. Finally, we have to consider the outermost operation, which is the star, so we have to apply the star construction, and the star construction was just adding a state that is initial and accepting to accept the empty word epsilon, and then for every transition that leads to an accepting state, we add a transition that goes back to every initial state. So the B was the transition to the accepting state, so we add a transition back to this initial state and 1 back to this initial state here. And we obtain an automaton for the regular expression a plus b followed by b and the whole expression start. This automaton, of course, looks extremely complicated. This is a much simpler automaton accepting the same language. If we have a closer look at the language, we see that this regular expression says that the first letter can be an A or a B, let's say it's an A, and then we have to have a B. And then because of the star, we start all over again, so we can again have an A followed by a B, and then we can start again, and then we might have a B followed by a B. And what we realize is that actually this regular expression defines that every second letter has to be a B. The B has to be at all the odd positions in the word, if we start counting at 0. And this can be easily recognized by this automaton here, because it just starts in the initial state that's also accepting, and then it doesn't care whether it's an A or an B, but the second letter has to be in B to go back to the initial state. And this process can be repeated arbitrarily often. So this automaton actually accepts all the words that have a B at each second position. Having first constructed a rather complicated automaton for this regular expression, and now having a much simpler one, you might wonder whether this is always possible, and this is the topic of one of the further videos, how to actually minimize automata.